Hi, I'm Stephen from TEFAT in Sydney, and today I'd like to do a statistics presentation, the calculations of confidence intervals, Z statistics, t-tests, and the p-value test, okay? And I intend to put the time of each test, so if you wanted to watch the p-value test, you'd know the time and you could just watch the p-value test. So we're going to start with confidence intervals. What confidence intervals are, it's a range of data that the population mean falls in a sample, okay? It's different to confidence level, which is the percent confident you are that the population mean is in that range. So here's an example of a range here, the final one with mu given by the population mean. That's a Greek letter mu. It looks like a back to front U. The population range falls within that range, okay? That's the confidence level. And confidence interval is the actual it's the actual how the data is spread from the population mean, okay? And so the range in which the population mean can fall in, okay? And for example, 174.2 centimetres and 175 centimetres. So we've got this question, calculate a confidence interval with 95% confidence interval with the following data. Some statistics students at a university asked other students if they could survey their height because they needed to do this for an assignment. So the other students volunteered the information to cooperate. The statistics students wanted 95% confidence in the survey that the information, they wanted 95% confidence in the survey that the population mean would be within the confidence interval. 150 students were surveyed at the campus. Their survey mean was 175 centimetres and the standard deviation was 5 centimetres. A table of typical tests was provided to the students below. That's critical values. Now, I'll just make sure that you can see that okay. Oh yeah, there it is. Yeah, that's a table of typical critical values. But I'm going to show you how to calculate those from the Z table if you're not provided that. So at a 95% confidence level in that table, you select 1.96 as the critical value at 95% level of confidence. So that critical value is marked here 1.96 and negative 1.96 with 0 at the origin. That means that that area under the curve is 0.95 and the tails are alpha over 2. What we mean by alpha, it's the level of significance. How you calculate alpha? Alpha equals 1 minus the confidence level percentage. So in ours it's 95%. So alpha equals 1 minus 0.95, which gives you 0.05. That's the level of significance. And we know that the sample mean with an X with a bar over it is 175 centimetres. We know the standard deviation, the variation of the data from the population mean, the spread from the population mean is 5 centimetres, okay? So that's the formula for a confidence interval. what we're trying to find. It's equal to the sample mean plus or minus the critical value, that value there, 1.96, multiplied by the standard deviation divided by the square root of the sample size, which is 150 students. So we know all that. We just need to calculate the confidence interval. It's not as difficult as what you might think. Now, if that 1.96 critical value, if you're not provided with a table, I'll tell you how you get it. First of all, this Z distribution is cumulative. So you add up that left tail and that middle area, and that gives you 0.95 plus 0.25. I also should mention that level of significance alpha equals 0.05. For the two tails, you have to split it into two, divide alpha divided by 2, so 0.05 over 2 gives you 0.25. That's the area under that tail, and 0.25 is the area under the right tail. So you add up 0.25 plus 0.95 to get to that point there, and when you do that, you get a value of 0.975. Now you've got to go to the table to find the critical value. Say you didn't have it, and say you didn't have it provided in the question. And where's that 0.975? There it is. That's it. Now when you go along to the left, you've got this number called, look like it's 1.96, and to the top of that you've got 0.06. You use the left hand side of the table number and the top number to put it together. So put 1.96, 1.9 on the left, put the 6 there, that gives you the critical value. That's how you find critical values if you haven't been given a table. Sometimes you are given a table, which makes it a bit easier. So add up 0.25 plus 0.95 to give you that value in the table. Go along to the left, get the left numbers, 1.9, and the top number is 6. Put it all together, that's your critical value. So we know all this. It's just about plugging it into the formula. Confidence interval equals the sample mean, which is, we said, 175 centimetres in this survey, plus or minus the critical value, 1.96, multiplied by the standard deviation, 5, over the square root of the sample size, which is 150 students. So you just keep doing this. Use your scientific calculator if you have to put in values into your memory of the scientific calculator. Also, memory recalls it, and if you made a mistake with the memory, just use memory minus key on the, you might not have to use the memory, just round it to either 4 decimal places to get accurate figures, and then that the population mean, mu, will fall within this range. That is your confidence interval. So it falls between 174.2 centimetres and 175.8, because it's plus or minus, remember, an upper value and a lower value. So that's the critical value with that formula, and we calculated the value of alpha. It's only 1 minus 0.95 here. If it was a different confidence level, say 99, you'd go 1 minus 0.99. And we also worked out how to get critical values by adding up those two areas if you haven't been provided them in a table. So getting that area, going along to the left to the top to get the critical value, putting the numbers together. So I don't think there's much more to add for that. Now I'd like to get on to hypothesis testing, and we're going to start with the Z distribution, the Z statistic. I'll go to that particular question on my notes, read it out, because I didn't have enough space on the whiteboard. Just check the video recorder. Alright, so I made up a question. The owner of a tennis ranch, Jim in Texas, postulated that the average playing time of players is 50 minutes. He is considering a pricing strategy to give his members a $2 discount if they are off the court before the 1 hour traditional time for the court, so the court is ready for the next players, which assists with efficient turnover of the court. It's an honour system and is supposed to promote good-humoured banter to boost everyone's spirits and satisfaction of their tennis experience. Jim hires Jan, a member of the club, in a contract who is cluey with statistics because she uses stats in her pharmaceutical research. Jan complained to Jim that some players are dragging the chain a bit with court hire, and Jim agreed. So the first step is we've got to set up the hypotheses in hypothesis testing. So Jim thinks the average playing time is 50 minutes. So set mu equals 50, and as the null hypothesis, the main hypothesis, the one that you think is the case, and the alternate hypothesis denoted by either HA or H1 is mu is not equal to 50. So we don't really know the population mean, but we have to in a sample we have to consider that 50 minutes as the population mean, because we're testing it. We're testing to see if that's the case, and if it's not, we can reject that notion that the playing time is 50 minutes. So it's just going over the page. Jan sets a 95% confidence level survey, so the significance level again is 0.05. Remember, we calculated by 1 minus the confidence level. 1 minus 0.95 gives you 0.05 for the alpha value. And so you draw a distribution curve again with 0.05 over 2, split the level of the significance into 2 because there's 2 tails. If you're only doing a one-tail test, if the data is only going in one direction, you just leave 0.05 as is. You don't consider sampling the left tail. You're not interested in sampling the left tail. And that can happen if you're looking at a target number and you're not interested in sampling this area because it has no impact on a business decision. It might be just a one-tail test where the area under the curve is 0.05 and at 95% level of confidence that you think the population mean is in this range, okay? That range between those two critical values. So again, if you haven't got a table, you add up 0.25 plus 0.95 to give you that area under the curve. You look it up to get the critical value. Again, we've got the same critical values as the confidence interval. It's quite a common test, 95%. But now we have to calculate the Z statistic. So we've set up our hypotheses. We've marked the level of significance, drawn up a distribution curve with the critical values and the tails. Area under the curve is that, 0.25. Now we have to calculate the Z statistic, knowing that 50 people were interviewed in the survey, and the sample mean is 48, mu is 50, and standard deviation is 12. Okay, so now we're going to calculate the Z statistic. It's 48 minus 50 over 12, so the sample mean minus the population mean over the standard deviation divided by the square root of the sample size, 50. So you go ahead and calculate the Z statistic, and it gives you a value of negative 1.1786. Now you have to compare or place that Z statistic in that range of the distribution and compare it to your critical values. Now, I'll just step over here. Negative 1.1786 is a lower number than negative 1.96. So that means that Z statistic falls in the left tail. And we know that if it does, we reject the null hypothesis that the population mean isn't 50 minutes. But if the Z statistic had have fallen in that range, the acceptance, what's called the acceptance region, so that's the acceptance region from that critical value to that critical value. And those are your rejection regions, okay? So you reject the null hypothesis if your Z critical value falls in the rejection regions. So ours did go into the rejection, and the correct terminology is fail to accept the null hypothesis. So in effect, we've selected the alternative hypothesis denoted by HA or H1, that the population mean isn't equal to 50. Now, we haven't just finished. We have to put this in words. Just put yourself as a statistician working for a business, and it has to be a professional business report. You have to give adequate conclusions, that you're just not some numbers boffin giving the board of director or a manager this. You have to say that, explain that in our sample, just to explain it, the survey a bit in layman's terms for the person who you're doing the survey for. Just state that we reject the null hypothesis, that's in our survey. So in fact the playing time of the average tennis player is not 50 minutes, and that discount scheme might not work. But at any rate, I just put in my example that Jim did put the discount in anyway for the tennis club members, and he had 2 tennis courts with a hooter which were a bit stricter, which gave the time of the tennis court. So don't just skip on to the question. Give a good conclusion, or you'll lose marks. So hypothesis testing is methodical. Your methodology is you set up your hypotheses, read the question carefully, set the level of significance, find the critical values, find the Z statistic. It's a normal distribution, so the Z table for the critical value. Find the Z stat, compare that to the critical values, which range it falls in. Is it higher than that, or is it between that and that value for acceptance, or is it less than that for rejection? So comparing your Z statistic with the critical values, and whether it's in the acceptance region or rejection region, we either accept the null hypothesis or reject it. More often than not, we accept the null hypothesis, but sometimes it's we reject it in the samples. So don't forget about that, finding the critical value, adding up that area and that area to there, giving you 0.95 plus 0.25, that area under the table, going to the side, the left numbers, the top number, putting it all together to get 1.96. Sometimes, as I mentioned, you get a table. So I think that adequately covers a two-tail test, hypothesis testing. Sometimes there's only one tail. Now, if it's a one-tailed test, the equal sign will always be in the null hypothesis. An example of a one-tailed test is HA where mu is greater than 50. Okay, that's just the alternative hypothesis. So that means the extreme data is only skewed to the right. That's a giveaway that it's a one-tailed test. Or another one-tailed test would be the alternative hypothesis where mu is less than 50. And in that particular example, the null hypothesis would have to be, for that one, it would have to be mu greater or equal to 50. And with that one, if you had that one-tailed test to the right, so that's a left-tailed one. If you had that right one, then the null hypothesis would have to be population mean less than or equal to 50. Okay, yeah, that's correct. So a hint, a clue to work out whether it's one-tail or two-tail. If it's not equal to, it's a two-tail test, but if it's only a greater than or a less than sign, it's indicative of one-tail test in the exams and assignments. So on to the next question. I'm going to do the P test now, and there it is. It's on this whiteboard. I'll just get this, put it on here, make sure it's okay here. Did have problems with this before. Right, that's okay now. Let's double check the video recorder. Okay, now p-value tests are a bit different. They do use normal distribution or t-distribution, depending on the test. Now, that brings me to what's a t-tail test. It's, even though we're talking about p-value, it's a sample size less than 30, and a normal distribution is a sample size greater than 30, because you can still get t-tests that use the p-value method. So we had to define t-test, sample size less than 30, and an I'll just read this out. An auto accessory retailer is considering a 10% discount sale for a month and may consider extending the sale for a quarter if turnover increases to substantially lift revenue. At the same time, advertising is increased on a radio station that they're partnering with. The retailer is partnered close to a retail radio station who advertises the sale. People in Albury were given discount vouchers at the store in a trial of a month, but the customers in Wagga Wagga weren't given discount vouchers but still heard of the advertising campaign on the radio. The auto accessory retailer is about to conduct a survey on customers in Albury about their response to discount vouchers given at the store. The store discount voucher scheme will cost quite a lot of money, and the marketing manager wants to know if the marketing strategy will substantially lift sales. If the store discount strategy is successful, the marketing manager will make it available to all towns in the radio station operating area, not just for a month, but for a whole quarter, possibly longer. The customers of Albury are surveyed. The question is, will you be likely to spend $150 or more per month as a result of the 10% discount? I set the I just set it the H0 equals 150 actually, and H1 mu is not equal 150. Sorry about that. So you set your hypothesis, which is H0. I'll just write it in. Didn't have much space. It should be here somewhere. Maybe not. Maybe I left that out. So here it is. H0, the population mean equals $150, and the HA is mu not equal to 150. So it's a two-tailed test. Now, p-value, it's not that difficult, but hints that it's a p-value test, if you're not told it is, it sounds very convoluted and complex and double-layered. They'll probably just ask you to do a p-value test, but sometimes when I was at uni, they didn't even say that you had to select it, and they didn't even say do a p-value test. So how the p-value tests work is, first of all, you've got to find a p-value, which is the probability that the significant data is skewed towards the end of the tails, and compare it with just alpha. And you already have been introduced to alpha level of significance, so the probability that I'm just going to get to how you calculate that. It's not too difficult, but before we get to that, you still have to calculate the Z statistic, because this time around the value of your Z statistic is actually your critical values, which is different to a normal Z statistic test. So this time around your Z statistic is your critical value, okay? Right? So you have to get used to this for p-value tests. So the Z statistic, first of all, let's go over some of this data. The sample mean is $140. The standard deviation is only $3, the variation from the population mean, and the sample size is 100. So you find the Z statistic. The population mean 140 minus the sample mean 140 minus the population mean 150, 140 minus 150 over the standard deviation 3 over the square root of the sample size. So it's the probability that the data is skewed towards the tails. P-value, but we haven't calculated p-value just yet. We've only just got critical values. All right, that's the step we're up to now. Now we're going to, so we got that negative 3.33 in our Z statistic, 3.33 positive there, and now what you've got to do is go to the Z table, because this is normal distribution, n is 100, So n is 100 is greater than 30, so it's just normal distribution. Now you have to go to the Z table and find an area for that critical value under the curve. Your area, all these figures are areas, okay? Now we have to find our area. So how you do this, that 3.33, you split the number. 3.3 is on the left hand side of the table and on the top is 0.03. And so I'll just point that out. 3.33, right? We got in our Z statistic, and that 0.03 on the top. So that value there is 0.9996. Okay, that's our starting point. And I've just written it on the right board as well. So that's the area. We found that from the critical value, right? We start with the area under the curve there, which is in the middle range between those confidence intervals. So that area, 0.9996, is between there and there. Now we have to find the area under the tails to get the p-value. So the first step is 1 minus 0.9996 equals 0.0004. Now you find, well, I should say 0004. So 1 minus 0.9996 equals 0.004. That's the area of both tails, right? Under both tails. But you have to split it into two tail. You have to find the area under just one tail, so you split it. You divide that figure by 2, which is equal to 0.0008. That is your p-value. That's your p-value. And you compare the p-value to alpha now to make your conclusions. So our p-value is quite small, 0.008. So 0.008, that's 0.008, actually that's a positive number. I might have thought that was negative. So if it's 0.0008, we actually, that's the acceptance region. Acceptance region. I might have had this written down wrong. And this this is the rejection region, and that one too. So I might just rub this out. It's just. Oh yeah, no, that's right. We do accept the null hypothesis. So, oh sorry, I'm doing the traditional method. No, that's the traditional method. Now we're getting confused. We're comparing the p-value with alpha. You can calculate it by the traditional method, but we're comparing that p-value directly with alpha, right? So 0.008 is much less than 0.05. Rub that out as well. Is much less than alpha, right? So if p is greater than alpha, we accept the null hypothesis. If p value is less than alpha, we fail to accept the null hypothesis. So in effect, we take the alternative hypothesis. So in that data, that sample, we take the alternative hypothesis, okay? So that means that the significant data in the survey is skewed towards the tail. The probability of the data, significant data going into the tail is quite high. So the discount strategy of the marketing manager won't lift sales to $150 per customer at all. And they might need a different marketing strategy or a new sample. So sorry about that. You still can calculate that with the traditional method with critical value, but in a p-test you're directly comparing the p-value with the alpha value. Greater than, accept null hypothesis. Less than, fail to accept the null hypothesis. Take the alternative hypothesis when you compare p and alpha. Okay? So just to sum up, we got the area under the curve with the critical value, right? Using that, we get the area under the curve. You go 1 minus 0.996. Why? Because that 0.996 is here, area, between there and there. And first of all, you want to get the area of the tails. But because it's a two-tailed test, you've got to divide it by 2. If it's just a one-tailed test, just leave that as is, and that's your p-value. But because it's a two-tailed test, we have to split it into 2 to get our p-value, okay? So p-values are quite favoured in the real world with statisticians. They like the flexibility aspect of them and ease of understanding with people with a limited knowledge of statistics and setting, choosing your own significance, that sort of thing. And now we have to get onto the t-test. The t-test isn't difficult. It's the one thing different about is the degrees of freedom if you've been introduced on the left hand side of but the t statistic formula is the same for a z test, but the table is different, obviously, the t value. So I've got to clear a board here. I'll just clear this one and write up the new question. I won't have time to clean it with whiteboard cleaner. Just one more test to go and we're finished, and then I can go over a few notes on the PC, depending on how long you want to stay. A t-test question. So this is a t-test. I'll read it out. You as a cafe customer have been asked by Fernando, a cafe owner, to do a survey on average table time for customers. He thinks the average stay is about 24 minutes. If it's 24 minutes, if it's 24 minutes, he can cope with space in the existing cafe, but the stay is significantly longer than, if the stay is significantly longer than 24 minutes, he is planning to knock down a wall to a storage room, renovate it and extend the cafe at great cost. He needs more room, which is a costly renovation. But if the stay is about 24 minutes, he can cope with the existing room. Fernando started the survey himself before getting the assistance from you. He asked 15 of his best customers, who are associates who are almost friends, about their average stay and plans of possible renovation. So 15 is your sample size. Because 15 is less than 30, it's a t-test. The customers volunteer the information and don't mind if he records their approximate stay in minutes, who think it's part of his business decision and they want the cafe to improve, as sometimes they wait for tables on busy weekends themselves. Now, a T distribution also is flatter than Z. Mark your critical values, the 0, the origin. Yeah, so flatter, push down with less sample size. And you're assisting Fernando now, so you want a survey at the 99% confidence interval. So 99% not confidence interval, confidence level that the population mean falls within that range. So I haven't marked the critical values just yet. We'll get to that. So that means that the alpha value is derived by alpha equals 1 minus 0.99. This time the alpha value is 0.1 this time. Just check that on my calculator. I don't mind checking because we want to get the correct answer, obviously. 1 minus 0.99, 0.01 actually, yeah, that's 10%, that's 90% confidence, so 0.01 is the alpha value. Sorry about that. 0.1 would be 90% confidence. So now you aren't interested in people below 24 minutes, this average time. So Fernando thinks the population mean is 24. So these are hypotheses. The null hypothesis is mu equals to 24. And the alternative hypothesis is mu greater than 20. Oh yeah, sorry, we made this a one-tail test, so is less than or equal to 24, and the alternative hypothesis is 24. So that's indicative of a one-tail test because the direction of the data is going to the right tail in the null hypothesis, that the one you want to test. So yeah, one-tailed test, you aren't interested in people below 24 minutes because they don't have a bearing on the survey, the business decision, the possible plan of renovating, people just ducking in for a quick coffee. They don't have a bearing. It's these long stayers that the people with the long staying time you're focusing on that you want to measure. Yeah, the quick 5-minute people are okay. We don't have to. We're not concerned with them. We're concerned on the people maybe overstaying the welcome mat and the cafe a little bit. So it's a one-tailed test. Now we've got to set a level of significance. We have 0.01, and we've got a sample mean of 28 minutes and a standard deviation of 5. So sigma equals 5. Sometimes standard deviation is not a meagre, it's denoted by just little s. Remember that's your sample mean. So now we've got to go and calculate our t-statistic. The t-statistic formula is exactly the same as the z one. So it's 28 minus 24 divided by standard deviation over the sample size, which is only 15 because it's a t-test. And that's your t-stat. Now we, after calculating all this out, and I don't have time to do it now, helping you step by step, I mean, you know, you should be able to calculate that. Just use the scientific calculator and put it in. Use the memory if you have to. So we get 3.1. We get I will state that the numerator is 4 over, and the denominator is over 5 over the square root of 15. 3.10 is our test statistic. Now we need an acceptance rejection region. So we've got to get the critical values. What are they? Rejection. Now we don't know the critical value just yet. We've got to find that on the table. So this time round, we know the samples. I've got to introduce the concept of degrees of freedom. Degrees of freedom, DF, is denoted by the sample size minus 1. So degrees of freedom is the data that is allowed to vary in the statistics definition. So when you find the critical values of a t-distribution spread, you go to the left-hand side of the t-table, and our degrees of freedom is 14. D dot F dot equals 15 minus 1 equals 14. So go to the degrees of freedom first. It's not too bad a t-test. There it is. So the left is the degrees of freedom, 14, right? And then you go along that row, and then up, you got to look up. Now, this is a one-tailed test at 1% significance. This is a 1% significance. So we have to select 1% for 1% level for significance. So that value is a critical value. So that's the top of the table. So one-tailed test, 1% significance, just there. So go down at that 14 on the left, and it gives you 2.624. It is the critical value. So I'll just write that up. The upper critical value is 2.624, and the lower critical value is minus 2.624. So we're 99% confident that the population mean falls within that range, and then we can accept the null hypothesis. But if it doesn't, if the Z statistic falls out of that range, we reject the, if it's in that region or that region, we reject the null hypothesis. So what happened in this survey? So 3.1 is greater than that figure. So it falls here in the right tail. Somewhere out here is 3.1. Somewhere in that shaded region. So that means we're in the rejection region. The significant data is skewed too much in that upper tail. And also I've made a mistake. This is a one-tailed test, so you don't have a lower critical value. We're only focused on that critical value there, 2.624. I'm really pleased I picked that up. It's a one-tailed test, so only one critical value. Yeah, so the data is skewed too much in that direction, the right tail. So we have to reject the null hypothesis. The correct statement by a statistician is fail to accept the null hypothesis. So we take the alternative hypothesis, that the waiting time, waiting time for people waiting for a table is more than 24 minutes. So that means that Fernando is left with the decision of possibly doing the renovation after all, because people are staying at the table too long and he needs the room. So, but I also wanted to mention that if it was a two-tailed test, and say Fernando was focusing on the 5-minute coffee customers as well as the long customers, he wanted to tailor his service for the quick coffee people, work out how to best serve them, and the long stayers in the night or the long lunch, and he wanted to tailor his service for both groups of people. Then a different type of test, H0, remember the equal sign is always equal, the equal or greater than equal to, or greater than equal or less to, or greater than equal, but the equal sign is always in the null hypothesis. Okay, so the alternative hypothesis is, in that situation, is not equal to 24, right? So that would be a two-tailed test with two critical values, minus 2.624 as well, okay? Just round it to two decimal places, really. You don't need a 4 decimal place critical value. So yeah, that would be a two-tailed test. Okay, so we've completed the two-tailed tests. How much does the less than does the sample size have to be again? 30. Okay, using the t-table, the formula is the same as Z. So t stat equals sample mean minus population mean over standard deviation over the square root of n, and find your t statistic, compare it to the critical values found in the table, which region it falls in, the acceptance or the rejection region. And remember about degrees of freedom in the t-test, on the left hand side where it's the sample size minus 1. Go up to the top to the correct level of significance. So that finishes that. I also wanted to go over a few little notes about regression. I won't keep you much longer. This is quite a long presentation, stats. Just make sure that's focused. Okay, zoom it in a bit. So, getting back, just recapping, summing up here. So, confidence intervals, a shorter calculation than hypothesis testing. It's the sample mean plus or minus the critical value multiplied by omega over the square root of n. The population mean is denoted by mu, the Greek letter. A lot of these are Greek letters, omega as well, alpha. Know what the confidence level is. That's 95% or 99% or 80%. Know the difference between that and the confidence interval, which is the range of the population mean. And for a two-tailed test, don't forget to divide alpha by 2 to split alpha into 2 areas under the tails. If it's just one tail, leave the significance as just alpha. Also, you know how to find critical values. Go to an area under the curve and go to the left to get the 2 left-hand numbers, put it together with the top number at the top of the table. For example, 1.9 and 6 is on the top of the table where level of significance is. And just whizzing through this for relevant bits. That was that sometimes you get a table, so 80%, the critical value is 1.28, 90%, 1.645, I've seen that. R1, and 99% the critical value is 2.58. But you know how to calculate the critical value by the cumulative method, where you add up the left tail and the area under the middle to give you an area under the curve. Go to that, and then you can go and so that's 0.25 plus 0.95 to give you 0.975. That's it. And then you go out to the left and the right to get your critical value. So what's the test statistic again? It's the sample mean minus the population mean over standard deviation over the square root of the sample size. The Z statistic and the T statistic have the same formula, which is good because you're in an exam situation. That's an example of a confidence interval range where mu is between those 2 values. You put forward that your population mean is between those 2 values. Yeah, that was the height example. Type 1 error is rejecting the hypothesis when it's true. Type 2 error is accepting a hypothesis when it's false. Increasing the sample size gives more accuracy of a good representation of the population. The Z distribution is a sample size over 30, but a T distribution only has a sample of less than 30, and it's a flatter curve. I want to get to some points on multiple regression because, so with the methodology, read the question carefully in hypothesis testing. Set up your hypotheses, the null hypothesis H0 and H1, or also called HA for the alternative hypothesis. Set your confidence level and level of significance, find that. If you're not given it, just choose 95% confidence and 0.05 as your level of significance. Calculate the test statistic, find your critical value from the table, draw your acceptance region and rejection region, but different in a p-test, where the test statistic is actually put in the graph as a critical value. And then you've got to find the area for the p-value. First, by deducting that area in the middle from 1. You know the critical value on the p-test. So then it's a matter of finding the area under the tails. Yeah. And then if it's a two-tailed test, you've got to split it into two. That's your p-value. And then comparing it directly with alpha. So there's the test statistic is your critical value. That's how a p-test is different. Now also with your a two-tailed test, if it's greater than or less than, it's dead giveaway that it's a one-tailed test. But if it's not equal to and the alternative hypothesis, it's indicative of a two-tailed test. So that's just some steps you've got to take in your hypothesis testing again. Have a real clear-cut methodology, what you're going to keep to tackle these questions head on. But I'm just trying to get to, yeah, because I've made this in really big font for you, I'll just get to I better get to multiple regression, because don't forget to put full conclusions. Put yourself in the role of statistician. This is interesting. The 1948 USA presidential election, when Harry Truman beat his opponent Dewey, the Republican, and confounded the statisticians. The sample was on the landlines, which favoured the Republican Party for some reason, and they were so confident that Dewey won, the Republican, that they published a newspaper article in the 1948 presidential election. That's remarkable. When actually Truman had won that year. Yeah, just trying to get to multiple regression. Sorry. Quick. Don't forget degrees of freedom and the t-tests. The sample size -1 as you do degrees of freedom, how much the extreme data can vary. Oh, here it is. I finally found it. So with multiple regression, it's straight curves, straight lines where y equals a plus mx. So a is your y-intercept and m is your gradient and b is your independent variable and y is your dependent variable. Y equals a plus m, depending what algebra you use. The y equals the y-intercept plus the gradient of the line multiplied by your independent variable, dependent variable on the left. So it's a number of factors, say factors affecting someone's salary, their age, their experience, and their qualifications. So each of those factors is a straight line. Some of those factors can work together, and sometimes the straight line factors are independent. That was the algebra I was looking for. Y equals ax plus b. But in multiple regression, it's all those straight lines are put in together. And then this time round, you get this long formula. So b is the slope of that particular curve. b1 is the slope of the next curve. x1, x0, x1, so on is the independent variable. and epsilon, which sort of looks like an E shape, is random error in multiple regression. But what you have to do in multiple regression is read a printout. When I was at uni, we had to read printouts of things like the mean, the standard deviation, beta, the slope of the lines, the sum of squares. Ask the lecturer what sum of squares is, arithmetic mean. So check which parameters you have to know in multiple regression. Also, there's just some other terms. Primary data is collected by organisations intending to use it. Personal interview, mail questionnaire. Secondary data has already been collected and collated rather. For example, ABS data. And so statisticians have to be careful with their data, poor or misleading visual presentation, how the sample is conducted, misleading comparisons, those type 1, type 2 errors. Discrete data is data in units, continuous data is data in categories. So data is summarized in tables, graphs, bar charts, pie charts, and pictograms. Be careful to label your diagrams and axes. Also, frequency histograms are those column shape data spread, and sometimes with a line linking them up. A pyramid bar chart, look that one up. That's interesting in subjects like geography and where the demographics is spread out for two variables, like, for example, two sexes. Look up pyramid bar chart. Frequency histogram is a bar chart diagram. Frequency curve or polygon is a line connecting the midpoints of each bar. Define frequency polygon. So the central limit theorem follows a normal distribution. And remember that cumulative concept of adding up all your areas, like left tail and the middle area. That S data, that's just notes on how to use a scientific calculator. You might need to use one or Excel for some of the calculations. Correlation, data is positively correlated, could be negative correlated. For example, if it's inverse, price is inverse demand in economics, so it's negatively correlated. Or it could be positive correlated, like when income goes up, so does savings and consumption. Positive is upward sloping, negative correlation is downward sloping, such as a demand curve. Now, back to regression, you're looking for a line of best fit in the data. And have a look at a scatter diagram in regression, where the data varies from that kind of straight line area. So this presentation has been given by me, Stephen Mack, in Trifolium Economics and Financial Accounting Tutoring. And that's the mobile phone of the business. I do accept Zoom as well if you're overseas, and Yeah, challenging stats, but I actually enjoy it. If you just keep to a methodology in your tests and keep structured, and just know the concepts, the difference between the P test and the Z test and the T test, yeah, it's enjoyable. You get a lot of satisfaction out of getting a credit in statistics. So thanks again. Bye.